morning, everybody. Okay, I hope everybody's doing okay. I've already been up for quite a while today. So today we're gonna have a little bit, I have three pages of like lecture notes, which is about half a lecture, but I think it's gonna be faster than that to wrap up activity coefficients and then introduce activities. And then we'll do an example, taking some data. It's problem 9 in DeVoe. So you have the problem and you have the solution you can look at, but I want to go through doing it in GRACE with some examples and the kinds of things you would be up against in reality doing stuff. I think it's always good to do a calculation, in other words, in GRACE, than doing things by hand. So we'll see how to do that. Now, does anybody have any questions? Okay, so typically in physical chemistry, activities are defined early. What's an activity? An activity is a unitless real concentration. And this is kind of the way it's explained in freshman year. In DeVoe's treatment, they take a different tack in that they define things thermodynamically exactly, and then we say that the chemical potential in an ideal system exactly depends upon the mole fraction. And then we start applying real systems to that. So we basically modify that mole fraction into, let's say, fugacity, right, for a gas, or the activity coefficient times the mole fraction to get an effective mole. So in other words, DeVoe builds it up kind of from an exact system, and at the end, we end up with activity. So we come at it from a different direction, but we're gonna define that activity today. So that'll kind of get us to the point where we can start doing things like equilibrium constants and so on, and reactions. Last time, the important takeaway was that the activity coefficient, which we've been spending a lot of time talking about, is the fugacity over the mole fraction times the pure reference fugacity. So this is for a gas, and remember, very often we think of the fugacity as an effective partial pressure. And the first, so this is kind of like an exact definition, but very often if we're not dealing with unusual pressures or temperatures, the first approximation to this a common approximation would be that the fugacity is the partial pressure. So if we have a gas that behaves a lot like an ideal gas, or we're at a pressure that's not too high, say less than, say, 50 bar or 100 bar, then we'll make this substitution. And that makes it a little bit more real for us. Now, and last time we finished up by talking about how can we find the activity coefficients from measurements, and we'll do more of that today. There's another way, or let's say there's another problem that arises which forces us, or allows us, I should say, to solve it using the Gibbs-Duhem equation. The Gibbs-Duhem equation is a very, very powerful equation that relates the chemical potentials. So let's think about the activity coefficient of B. This is the solute, right? And what if B is non-volatile? Now, what we did last time is we found the activity coefficient of the solvent through the fugacity or partial pressure of that species above the liquid, right? So, and that's because we assume the solvent is volatile. So there's a relationship between this mass transfer between them, and it allows us to use the partial pressure or the fugacity, right, above the solution to figure out the activity coefficient of the solvent in the solution. But if the solute is relatively non-volatile, we can't do that. This might be small, it might be fluctuating. You know, there's just, maybe it's just not a well measurable thing. Okay, so as long as the solvent A is volatile, there is a way around this. And it's kind of similar, it's kind of similar to the way that the mole fraction of B is 1 minus the mole fraction of A in a two-component solution. There's a dependency there. So there is also a dependency between what's going on with the solute in the solution and the solvent in the vapor phase. And we use Gibbs-Duhem to do that. So what we need is we need A and B miscible in all proportions. And only A needs to be volatile for us to do this. So maybe this is sugar and water. Sugar is not actually miscible in all proportions, right? Because if we took a kilogram of sugar and 2 drops of water, we don't have a solution. But realistically, for a normal range, this is true. Okay, so if the solvent's volatile, we can measure the fugacity or partial pressure in equilibrium with the mixture, and then find the activity through this way that I just mentioned. All right. And what we do is we use Gibbs-Duhem to then find the activity coefficient of the solute. It's not, I'm not saying that this is super straightforward, right? But mathematically we can do it. So we're going to see how we can do it. And we're not going to do this directly, but we're going to see how we can do this. All right, so Gibbs-Duhem says the mole fraction of A d mu A plus the mole fraction of B d mu B equals 0. That's Gibbs-Duhem. And if we use a conventional solvent-based free chemical potential, solvent-based chemical potential for this, then we can take the total differential of this. The first term is a constant, right? So that goes away. And for some reason, when I wrote this in my notes, I reversed the order of the log and the d. So I have to be careful so I don't confuse you. There should be a d. Hold on here. Show you what I missed here. There should be a d here. All right, so then we get RT over XA, dXA, right? So we're doing that identity only for the mole fraction part, not for the activity coefficient part. All right, for the solute, we use the fact that the mole fraction of B is 1 minus the mole fraction of A, along with the definition or the derivative of this. Now, the standard state for the solute is different, right? But again, this is a constant, so we take the derivative of it, we can ignore it. So what we end up with is basically the same kind of expression. So this is where that identity comes in, right? So what I want to do is I don't really care about this factor of mole fraction of B, but I want to get the dependency, in other words, the derivative of the mole fraction in terms of A, right? So when I integrate, I can do this. And because of this, right, the change in mole fraction of B is just the negative change in the mole fraction of A. So that is the kind of dependency that lets me fix this. And if I put these two expressions into my Gibbs-Duhem equation, I get this. And this all equals 0. again. Hold on, I made a mistake in my notes. I gotta fix this so I don't blow it next year. All right. All right, so if we collect terms, we get something like this. All right, this first part here equals 0, right? Because of this. So we use this twice. That gives us a much shorter, simpler expression, right? So I get the d log of the activity coefficient of B equals a ratio times d log. So this is the pseudo foggy intuitive relationship between the activity coefficients. You know, they're dependent on each other because they're in the mixture together, right? So in order, the first thing is we have to realize that the activity coefficients are a function of the mole fraction, right? It's not a constant, it's dependent on the mole fraction. So when we do this integration, we're going to get, let me go ahead and integrate both sides so we can see what this looks like. So we're going to integrate the mole fraction of B from 0 to some other value of mole fraction of B. And, oh, I'm sorry, not 0, 1. And we're going to do the same integration on the other side. Now, remember, we can switch those integration limits from mole fraction of B to mole fraction of A if we want to, right? Because they depend upon each other. So the right-hand limits really can be expressed as the mole fraction of A. But what we get on the left-hand side is log of 1 is 0, right? Log of 1 is 0, so we only get one term. The activity coefficient of the solute at a specific concentration, but the other side retains the integration. So we have this thing that we have this same kind of issue that we had before, where we're gonna, and I'm just gonna draw, this is really a cartoon, right? But we're gonna have the XA 0 to some XB prime number, which is 1 minus XA prime, right? So we're really integrating from XA equals 0 to some other XA value. We have this function, whatever it looks like. We find the area under the function, and this equals the log of that activity coefficient, right? So this is that problem. Basically, it's very similar conceptually to that problem we had on the test, where you have to do an integration for every value that you're interested in, for every mole fraction that you're interested in. but it's doable. I believe DeVoe has a example question like this. Okay, so that the takeaway from that is basically, even if the solute is non-volatile and you can't measure its fugacity and thus get the activity coefficient of the liquid, you can get it this indirect way, which is kind of a pain in the ass, but you can do it, right? So if you're interested in that kind of thing, it's definitely doable. All right, so now this brings us to the definition of an activity. There's only one more thing that we have to worry about within the activity. So basically, the activity is going to be our activity coefficient times our concentration factor, right? We saw this before last time. Remember, we saw the chemical potential, or the we saw the fugacity was some activity coefficient, the phi or the gamma, times the concentration factor times a pressure factor, which we haven't talked about, right? So this is going to account for everything that we've talked about. Here's how we define the activity rigorously, right? The effective concentration or activity is always going to be a difference of chemical potentials. And this is a bit of a compression, right? Because that chemical potential of species I is going to be some function, right? It's been all the stuff that we've looked at so far. We're going to insert these things in here. So this is, it's not misleading, but it's just a compact form of this. The other way we can look at this is written in terms of the activity. We can say that the chemical potential is some standard chemical potential plus RT log of the activity. So that activity is actually going to wrap up everything we've talked about. All right. So let's look for a second. The last thing we want to look at is the pressure dependence. So let's look at that, how we can come about that. This standard chemical potential is defined as the standard chemical potential at some temperature and pressure. So this depends upon the choice. It's not really a choice. It depends upon the standard state, right? We really don't have a choice when we define the standard state and the composition, right? All right, so this refers, we can go back and look at the list on page 273 of DeVoe. Let me look at it to make sure I know what we're talking about here. That gives us things like this. Right? So what we're doing now basically is we're wrapping up all the things that are in that logarithm term, the mole fraction, fugacity, activity coefficient, into I. We're just going to wrap that all into something we call the I. Now that we know what's in there, we're going to call all those factors together. I said I meant A, activity, right? And so other things are similar, right? We have that standard list of different situations: solvent in a solution, solute in ideal dilute, and so on. Okay, but the one thing we want to realize is that when this activity equals the standard activity, then the activity, I'm sorry, when the chemical potential of the species I equals the standard chemical potential of species I, then the activity goes to 1, right? So what this basically means, as things in their standard states have unit activity. In other words, they're stable the way they are. Right? And now I'm using stable kind of in a way that a freshman chemistry student might use stable. Freshman, before you learn a thing or two, you just use stable for a stand-in for a lot of things, right? And nothing happens because it's stable. But now we know this means thermodynamically stable, right? Its standard state is stable at that temperature and pressure. Okay. We have to talk for a minute or two about the difference between a reference state and a standard state, right? What's the difference between a reference state because they're easily confused. So the standard state chemical potential is the standard state at the standard pressure, right? That's why it gets that caret, because it refers to the standard pressure. These are equal only if the pressure for the reference is P naught. In other words, I might write it this way. DeVoe doesn't write it this way, but that would be kind of my shorthand. Okay, so let's define a pressure factor. We're going to define this with the big gamma, right? Because we always like to use a corresponding capital Greek letter to describe something that's similar to something we've already used for a small Greek letter. So we're going to define this large gamma, which is going to be our pressure factor, as the difference between the reference and the standard. So if the reference state equals the standard state, this gamma is a unit factor and it has no effect on our thing. So we could write, for example, the reference is the standard plus RT log times this factor, right? So these are just two different ways to write it. And further, we can write that the difference depends only on P. So this is purely a pressure factor. The reason we want to think about this way is that if our pressure is not unusual, and by unusual I say, let's say normal room pressures, right? Let's say less than or equal to about 50 bar, we don't worry about this. And we say that this factor is going to be 1. But if we include this in the activity, right, let's kind of look at the molality space for chemical potential. I have to say I'm not exactly sure. Well, I'm a little bit sure. Let's say it's not, if you look at this, it's not going to be exactly clear why, after spending so much time through most of chapter 9, using the mole fraction space, right? We use mole fraction for our activities, activity coefficients, concentrations, so on. Now, here at the end of this chapter, all of a sudden, to use for the example of how this works a little bit, DeVoe uses the molality space, right? I will say the reason this change is happening is that when we get to physical properties of solutions, colligative properties, molality is the concentration of choice because it's just experimentally easier to work with. So I think that's why this subtle change has occurred. All right. This this little step here, or this little statement here, it's kind of innocuous, I think, in DeVoe's treatment, right? But this is kind of profound in that this is really the kind of relationship that defines activity, activity coefficients, and concentrations. Okay. So it can't be overstated in the use of these things. This right here kind of wraps up chapter 9, right? We have rigorously defined the chemical potential through the concentration units, really mole fraction, and we've stated how we can use molality, for example. It's really no different. And then we introduced the activity coefficient to talk about non-ideality. But now we're going to generically talk about the activity, which however we express those 3 factors together, they're going to be defined as the activity. And for an element, or for a component in its standard state, the activity is 1, which kind of denotes a fact that that component does not want to do anything, right? It doesn't want to react. It doesn't want to vaporize. It doesn't want to crystallize. It just wants to be the way it is because it's in its standard state and it's happy. So that's unit activity. For interesting things to happen, the activity has to be different than 1, and we get reactions. So this is kind of the thing. And I think DeVoe's just a little bit understated about this. Okay, well, if we look now just at the activity in the molality basis, it's going to look something like this. Right, we have to state that we're in the molality basis. All right, and so this again is going to be this pressure factor, whoops, times the other stuff we're used to seeing. Okay. Or in other words, we have these three factors. We have the pressure factor, the activity coefficient, and the concentration factor, which is kind of what I said at the beginning, and the pressure factor is the last thing. Now, there is a list on page 274. This similar list we've seen for these different conditions for what these pressure factors are or how they work. But really all they do, I mean, literally all it does is inserts this giant gamma in the expressions we've seen before. And as I've said before, that I don't think we're ever going to see it unless we're specifically looking at the pressure factor, at least in which case we are going to be looking at high pressures or unusual pressures. We generally aren't concerned about this at all. So this essentially reduces to what we've seen before. Okay. But it is something to mention. All right. There's a little bit more, there is some more stuff in chapter 9, but we're going to ignore section 9.8, which deals with gravitational fields. It's kind of interesting, but I really have to pick and choose what I'm able to go into about. And then I'm also not talking about 9.6.3 specifically, if you come across that. And I also want to say that some parts of chapter 9, which deal with electrolytes, I'm going to move those to chapter 10. So I'll just basically in the PDF of these chapters, I'll just like circle this section and say I'm moving this to chapter 10, because as I mentioned before, I think it's easier to handle in the proper context. Is my video breaking up a little bit? Can everybody hear and see me okay?
You're good.
Okay. My own little video is kind of breaking up, which is weird. Usually it's the other way around, right? But anyway, all right. So now let's look at problem 9.9 in DeVoe. And I'm going to call this a problem map. Okay. So problem 9.9 has a table . It took me a while to figure out, DeVoe has this habit of putting the table on top. My computer really seems like it's churning for a second. Let me see if I can figure out what's going on with it. I think it's decided the load is like 1 million. And I don't know why. So let me quit a couple things and see if that makes it relax a little bit. Okay, well, it's just getting hard for me to do anything all of a sudden. Sorry, I just have to force quit a couple things. I don't know what. I don't know what specifically is causing the issue. Maybe that's a little bit better. Okay, so I apologize for that. So DeVoe's got this data that is, let's see if this is going to behave now. It's really not. I wonder why. Huh, that's weird. My preview app is causing my computer to be unhappy. My terminal too. This is very strange. Okay, so I'm sorry, I'm having trouble getting that preview up, but the data is, if you look at the data table, it has the liquid mole fraction of the solvent A, the vapor mole fraction of the solvent A, and the total pressure in kilopascals. This is the total. This is, you know, most of the time in a gas phase experiment, this is what is given to you as the total pressure, because it's pretty easy to measure the total pressure, right? All you have to do is put a pressure gauge in your system, and you know, partial pressures are hard to measure. So this is very often what you have for your data. So let's map out quickly what this problem is asking us to do. First thing it's asking us to do is tabulate the partial pressures of A and B. Okay, and of course the way we find this, right, and now we see why we use the Y for partial pressure of vapor rather than other books I've seen use an X with a V on it, and it's just not. I'm going to stop my video too. Maybe that'll help me. Anyway, it just is a little bit cleaner to do this. And the easiest way to find the partial pressure of B, if you think about it, is the total pressure minus the partial pressure of A, right? This is the easiest way mathematically to do this. So for this, we're just going to read the data and manipulate it in Grace. That's the easiest thing to do. Okay, part B is it wants us to plot PA, PB versus the mole fraction of A. And I've added some things in here. Why is my preview just came back to life after I killed it? Okay, that's weird. So in this problem, I would want you to identify the Henry's law and Raoult's law areas or behaviors. Draw a guideline for Raoult's law, right? Okay. Part C, calculate the activity coefficient for A and B. It turns out that A is methanol and B is benzene. Okay, so to do this, we're going to use partial pressure instead of fugacity. So we're going to assume the fugacity is the partial pressure. So in other words, this is going to involve a calculation like this. Right? And we have the pure partial pressures of B, 29.894 kilopascals and 44.60 pascals, right? So a kilopascal is basically to a bar as a torr is to an atmosphere, right? So chemists are either going to express partial pressures in torr or kilopascals, and the numbers are going to be kind of in the same neighborhood. All right, D, estimate Henry's law constant for benzene. The problem asks just for, the problem just asks for benzene, but I'm going to throw in A too. There's two ways you can do this. From the Raoult's law plot, we've talked about that. And kind of what I would call a ratio plot, where you do this Henry's law constant equals the limit as the mole fraction